next speaker is Pankaj Khandelwal, who will be speaking on an insight into garbage collection. He is a proud gopher and works as an engineering manager at Gamescraft. Please welcome Pankaj.
Hello. Good morning, everyone. Sound is clear? Okay. So today we are going to talk about basically garbage collection and how can we tune it for the better performances. Okay. So today's agenda is basically a brief introduction about the GC, basically how the garbage collection works. Second is how the memory is allocated in the GoLang. Third is the GC pacer, which is the basically garbage collector control mechanism. Another one is basically the GO's garbage collection is not the generational one. It's like concurrent garbage collection. So how that achieved in GoLang, what happens behind the scene. Next one is basically the Ballast. So it's a mechanism or hack that was created by Twitch. Basically, it's very popular in the Go world. Apart from that, we'll talk about the GC assist. And next one is basically the improvement that happened in Go 1.19. So Go 1.19 was recently released, and they did some optimizations on the GC. So we'll talk about that as well. So basically, the garbage collection, what it is, I think is there in every language, either we have to manually do it or the language does it for us. So basically, it's a mechanism, whenever we write a program, we need to allocate the memory. And once the task of that memory space is done, we need to basically deallocate it so that it can be further utilized. Next we are going to talk about the memory allocation and what are the memory components. So basically, there are two components, stack and heap. So whenever the process starts or the Go routine starts, there is a stack which is associated with every Go routine, and then there is a heap, which is basically the common memory pool for all the Go routines. So stack is basically dynamically sized in Go, dynamically sized. Basically, whenever Go routine starts, it has the stack size of 2 KB, and it keeps growing up dynamically as and when it is required. And it's basically works as the data structure as well, this is the LIFO data structure. The heap, basically, we'll talk about the heap. Heap is basically a bit complex area. It's kind of on-demand solution. So basically, whenever there is a process which demands some allocation, which does not fit on stack, so we it basically asks the heap to basically provide the memory, and then there is the allocation happen. So how does the memory, how does we decide basically what goes on stack and what goes on heap? So as of now, Go prefers to allocate on the stack. Stack memories are cheaper. Heap memories are bit costly. We'll come to that, why heap memories are costly and why stack memories are cheaper. So basically, whenever, let's say, there's a function call which happens, so on Go's stack, there's a new frame which gets pushed on the stack, and whenever the function scope is over, that basically frame is no more valid, and it gets deallocated. But on the heap, basically, it cannot be automatically freed. So basically, what happens, there is a GC or there is some mechanism that we need to run to basically deallocate that memory. So basically, how does Go identify whether a variable sits on a stack or the heap? So it does an escape analysis. So by the escape analysis, basically, compiler try to identify whether basically the variable or the memory that we are allocating has limited lifespan. If it has limited lifespan, it's try to allocate on the stack. Otherwise, it try to allocate on the heap. So next, coming into that, basically, I'll try to oh, explain like what happens to the pointers, like when like we have pointers in the program, what happens, like do they go into heap, and what's their impact on the GC. So as you can see, like there are like three functions that I have written. One is basically without pointer, which is basically just doing some basic calculation. Next one is like, yeah, with pointer. Basically, what it's doing, it's returning a pointer. Uh, the next one is like with pointer as an arg. It's accepting a pointer, and it's not returning the pointer, it's returning a normal variable. So what's the impact? So we'll just see some benchmarks and profiles. So this is like the first function where we are not using any pointer. We are just doing some simple calculation, and we'll just do the benchmarking, like what happens. So if you see at the below, basically the operation, like per operation time that this function is taking, like 1.4 nanosecond. In the second case, where we are using function as, basically I'll show the function as well, where we are returning a pointer, and we are running the benchmark. We saw that, see like each operation is taking like 11.89 nanoseconds. So it's around like 10x time, 10x more time this operation is taking. Like when we are using pointer, it's more expensive. Like the allocations are taking more time. And the third one is basically when we are accepting pointer as an argument, what happens in this case? I'll show the function as well. In this function, we are not returning the pointer, but we are accepting pointer as an argument. Here also, like it's the per operation time that we are utilizing is like 1 nanosecond. So it's also cheaper. So it's not that like if we are using pointer, it will end up on heap. There are like, in some cases, it ends up on heap. In some cases, it doesn't end up. Like mostly like when we are passing pointer down the stack, it doesn't allocate on the heap. But when we are basically passing up on the stack, it allocates on the heap. So that's the basic, like what is happening in the second case. Basically, when we are returning a pointer, what is happening in that case? So we'll just see the CPU profile. So if you see, like there are like multiple runtime functions which are basically invoked when like we are using this profiling, CPU profiling. We can see it in the flame graph. But on the contrary, like when we are not using pointer, we'll just see again. So it's not invoking any runtime functions, like not many runtime functions, like compared to like the pointer one. So what happens basically here? So you see like on the right side, like whenever a new allocation is happening, like it calls malloc GC functions, and like there are like on the left side you can find out like the runtime GC function are being called as well. So basically with heap, what comes up, like whenever we allocate the heap memory, there is like a GC that needs to run to basically free that memory. So that's about like heap and stack, and like how can we actually identify whether the memory is going on to heap or stack is basically by using the escape analysis, which basically you can do with like GC flex. So this is like some comparison that we did right now. Like without pointer, it's pretty faster, and but with pointer, every operation is taking more time. So as we discussed, basically, like sharing pointers up the stack results in allocations, but sharing pointers down ends up in the stack. So it's the general rule, but it's not guaranteed. Like mostly, like we need to use the escape analysis to basically identify that. So now what happens in GC, like how exactly the GC works, we'll go into that. So Go has an basically controlling mechanism which called GC pacer. How does that work? Like let's say initially there is a base heap size which is basically set at let's say 2 MB. So by default, like there is a Go GC variable which basically controls like when the next GC cycle should get invoked. So as it grows to 2x, like from 2 MB it grows to 4x, the GC cycles gets kicked in. So, like let's say post 4 MB, the GC size heap size got reduced to like 3. Next time it will kick in at 6. So that's how basically the GC pacer works. So the GC algorithm that the Golang has is concurrent. Basically, what does that mean? Like when it's doing the GC work, it doesn't need to stop all other things. It stops for the brief time. There's a phenomena which we call like stop the world. It stops it for the brief time. And then basically, there is some 25% of the CPU that gets allocated to the GC. For the rest, basically, rest CPU could be utilized in the application. So basically, there are the phases of like GC. So it uses like the tricolor algorithm, which basically consists of like mark and sweep phases. So how does the tricolor algorithm works? So basically there are 3 colors. Like heap objects are colored into like 3 colors: gray, black, and white. So initially, like when we start the mark algorithm, all the roots are the variable which like the program directly has access to, such as like the stack variables and the global variables. So it marks the basically root variables as gray. Then basically it picks the gray object and like then it try to identify what other references are there. It marks them gray, and the already gray objects which are there, it marks them black. So at the end of the process, whichever the white objects, basically they are the one which are basically candidates for like sweeping. So that's the basic algorithm that Go uses. Now basically, how does Go ensures like while it's doing the marking process, the new allocations or like the basically if there is any pointer which gets modified, how does it make sure like it doesn't sweep that? So what it does basically, whenever like the garbage collection process starts, it stops the world basically briefly for some time, and it turns on the write barrier. What that write barrier does, basically whenever a Go routine, which is basically modifying some pointer, what the write barrier basically marks the reference to that pointer as gray. So it could be rescanned. So that's the uses of the write barrier that's there. Again, basically, it's after turning on the write barrier, it starts the world and it starts the mark process, and the usual basically GC process kicks in. So that's the point of like the write barrier. It try to maintain the data integrity. So basically, the data points that are in use should not be swept. So that's the point of the write barrier, and that's how like Go achieves the concurrency. So there is this technique basically which was popularized by Twitch guys. Basically, this is called Ballast, which basically tunes in the GC. So let's say if your process or your program is doing like high memory allocations and deallocations, the GC cycles will get kicked in a lot of times. And at scales this frequency, like if you assume like most of the times like when the GC cycles get kicked in, 25% of the CPU is going into the GC, That's a huge cost that could be there. So how basically we can reduce it? So the 25% is the fixed cost, plus there is a variable cost as well, which I'll explain when I come to the GC assist. But as you can see the result, like the results of like applying Ballast into the program, basically without Ballast, the latency is like somewhere around like 99% latency, is somewhere around 1000 milliseconds. But post Ballast, it's around like 560. So that's like roughly 40% reduction. Same could be seen with the 90th percentile as well. So how does we do that? How do we do that? Basically, whenever our program gets initialized, we allocate a large chunk of memory to the heap. So basically, your base heap size gets increased. So as let's say if like initial heap size was 2 MB, the next GC cycle would have kicked it at 4. But let's say if we increase it to 200 MB or somewhere more, the GC pacer will kick in the GC cycle at 400 MB. So basically, that's how we reduce the GC cycles. Now we'll talk about like basically how this actually helps in reducing the latency. One is basically less number of GC calls, which gives more CPU time to the application. But there's one more thing that happens during the GC cycles. Basically, when there is a GC cycles, the Go routine which are basically allocating the memory to the heap, basically they are involved in GC assist process as well. So what the GC assist process does, basically it tries to basically assist in the mark algorithm, the mark and sweep. Basically, it tries to assist in the mark, and the work that a Go routine has to do depends on the basically the size of the allocation. So it can be assumed basically GC assists work as a tax. So why does Go do that? Basically, it tries to control the heap growth while the GC is in place. It tries to control the heap growth. So that's why GC assist is there. So Ballast benefits is basically reduction of GC cycle. 24% of the CPU that was going there is basically now we have to the application. Third is basically the mark assist, because in each GC cycle, mark assist is going there. So that's also basically more CPU available to our application. The next one is as like I talked about like the at scale. At scale, if like a lot of GC cycles and like GC assists are happening, then basically it means less CPU for our application. So we can avoid that. In our application as well, basically, when I was working at GoIBO, we used to have like lakhs of RPM, and like the GC cycles were in order of like 10K. So with we use this Ballast, post that like our GC cycle got reduced to 150, and we saw latency improvement as well, and the GC post time was almost same, because like marking is only marking the objects which are basically live. So the GC post time is similar, but GC cycles get reduced. There is a new enhancement that came into Go 1.19, which is called GoMam Limit. So basically, it's a safeguard for the OM. So let's say if your total container memory size is 100 MB, and after doing the GC, basically the next heap, the live heap size is 60 MB. So the next time the GC will kick in at 120 MB. But your container size is 100 MB, that it would result in crash. It might result in crash. So basically, what happens with GoMam Limit is like you can define a soft memory limit of like heap size. So what happens, let's say, if your container size is 100 MB, and basically we set the GoMam limit to 80 MB. So what happens, like when our heap memory is closer to 80 MB, the Go pacer, it tries to kick in another GC cycle. So basically, it tries to prevent the OOM crash that could have happened by utilizing the soft limit. It's the soft limit, it's not the hard limit as of now. So eventually, like, basically what might happen, like it might get crashed, but the probability gets lower. So that's about basically this new enhancement that was introduced in Go 1.19. So these are the certain references that I used for my talk. And that's about the GC talk that I had. Thanks.